Hello everyone, we're going to go over section 13.3, geometric sequences and series. Let's first go over the definition. A geometric sequence may be defined recursively as the first term is a and nth term equals r times a sub n minus 1, where r is called a common ratio. Since a sub n equals r times a sub n minus 1, we can solve for r. So r, which is a common ratio, is defined by a sub n divided by a sub n minus 1. Let's do some examples. Example 1, show that our sequence a sub n equals 3 times 4 to the n is geometric, and give the first term. Now the sequence is geometric if you can find the common ratio r. So let's first start out with that. So let's go with common ratio. The formula is a sub n over a sub n minus 1. And our a sub n is 3 times 4 to the n. And then a sub n minus 1 is 3 times 4 to the n minus 1. Therefore, our r is going to become 3 times 4 to the n divided by 3 times 4 to the n minus 1. So we can cancel out the 3. Now who's left over? So we have 4 to the n over 4 to the n minus 1. Now let's combine this together. So we're gonna have 4 to the n minus n minus 1. So this is gonna be just 4. So therefore, we're able to find our common ratio to be a constant 4. So yes, it is geometric. Let me box that. Now let's go with the first term. Is a sub 1, so that's nothing but 3 times 4 to the first, so it's going to be 12. Let's do another one. B sub n is 1 over n. So let's try to figure it out whether this sequence is geometric or not. So step 1, find a common ratio. And where our a sub n is 1 over n, and then a sub n minus 1 is 1 over n minus 1. Alright, so our r is a sub n over a sub n minus 1, which is 1 over n, whole thing divided by 1 over n minus 1. So this is going to be n minus 1 all over n. Now notice that that expression is not a constant. So that should tell you that this sequence is not geometric. So let me explain that part. So not a constant. And also, I want you to know that, yes, this sequence is not geometric. However, you can still find its first term. So our first term our b sub 1 is 1 over 1, so which will be 1. Let's go with the theorem. Nth term of a geometric sequence. For a geometric sequence a sub n whose first term is a sub 1 with a common ratio r, the nth term is defined by a sub n equals a sub 1 times r to the n minus 1. Next theorem is sum of the first n terms of a geometric sequence. Let a sub n be a geometric sequence with first term a sub 1 and common ratio r. The sum, the notation is big S sub n, of the first n terms of sequence a sub n is defined by S sub n equals the sum, k going from 1 to n, of a sub 1 times r to the k minus 1. And which in fact, that's going to add up to first term times 1 minus common ratio to the nth power divided by 1 minus the common ratio. Do not panic, we're going to do some examples next. So example 2, find the sum S sub n of the first n terms of the sequence, which is defined by 1 over 2 to the n. So first, let's try to understand what the heck is going on. So if I expand this sequence, what we're going to get is our first term is 1/2, comma. Second term is going to be 1/4, comma. Third term is 1 over 8, 1 over 16, and yada yada yada. And now what we want to do with this problem is that we're going to keep adding those terms all the way up to nth term. So let me just write it down. What we want is try to come up with the formula for this sum all the way up to nth term. So let's just call this guy S sub n. So what we want is try to come up with a formula to describe this sum. Now going back to the previous page, let's just recall that our S sub n was defined by sum k going from 1 to n of a sub 1 r to the k minus 1. So this is basically telling you that if I could express this sum in terms of this form, then our S sub n is going to add up to a sub 1 times 1 minus r to the n over 1 minus r. So let's get to work. So if I express this sum in terms of a sigma notation, that will be sum k going from 1 to n of 1/2 to the k. Do you agree with that? Because when k equals to 1, our first term is going to be 1/2. K equals to 2, our second term is 1/4, so it works. But this expression does not look like this guy right here. So we need to make it look like that. So let's just take a look at 1/2 to the k. Now, do you agree that this is the same thing as 1/2 times 1/2 to the k minus 1? Because when I combine these two expressions together, you need to add the exponents. So there is that invisible 1 sitting there. So if I add the exponents, I get k back. So now I can rewrite this sum as a sum k going from 1 to n of 1/2 times 1/2 to the k minus 1. Now this is exactly of this form, so we are good to go. So this guy plays the role of a sub 1, and whoever that's got an exponent attached on it, that will be your r. In this case, your a sub 1 and r are exactly the same. But anyway, so let me just write it out. A sub 1 is 1/2, and then our r is 1/2. So therefore, our sum, let me just change the color, S sub n is going to be, formula for that is a sub 1 times 1 minus r to the n over 1 minus r. So which is 1/2 times 1 minus 1/2 to the n, whole thing divided by 1 minus 1/2, which is 1/2 times 1 minus 1/2 to the n all over 1/2. Now I could cancel this 1/2 out, and it looks like our formula for the sum, it's going to look like 1 minus 1/2 to the n. So therefore, our answer S sub n is 1 minus 1/2 to the n. This formula is pretty cool because if I want to keep adding 1/2 to the first plus 1/2 to the second power plus 1/2 to the third power let's just say all the way up to 1 over 2 to the 50th power. Well, you don't have time to be adding those numbers in a calculator. But this formula right here, as long as you replace your n with 50, boom, there's your sum. Let's do something a little bit different. So example 3, find the fifth term and the nth term of the geometric sequence whose initial term is 5 and with the common ratio of -1. And I would like to do maybe 2 or 3 examples of this. So let's just call this problem A, where A1 is 5 and R is -1. So let's first look for the nth term of this geometric sequence. If I could come up with the formula for it, then the fifth term is very easy to find. So let's just recall this. A sub n, nth term of the geometric sequence, is defined by a sub 1 times r to the n minus 1. We're going back to the very first page of the definition of a geometric sequences. So what we're going to do is we're going to follow this formula. So a sub n is a sub 1 times r to the n minus 1, which is 5 times -1 to the n minus 1. So our nth term is given by 5 times -1 to the n minus 1. Now we got the general formula, then we can easily find any terms that we want. So in this case, they're asking for the fifth term, so plug it in 5 in place of n. So 5 minus 1 is 4, so that means what? That's going to be +1. So the fifth term is going to be 5. Let's do another one. We're going to do the same thing. I want you to come up with the nth term of the sequence and then compute the fifth term of the sequence. So first, a sub 1 is 0, r is 1 over pi. So again, let's follow this formula. A sub n is a sub 1 times r to the n minus 1. So our a sub 1 is 0. Alright, so 0 times anything is 0. So our formula for a sub n looks kind of weird, but that's okay. Our a sub n is always going to be 0 no matter what the value of n is. So with that said, a sub 5 is also going to be 0. Maybe that was not too exciting, so let's take a look at another example. Let's try a sub 1 is 1 and r is -1/3. So again, I'm going to write down the formula. Right, now plug and chug. A sub 1 is 1, r is -1/3 to the n minus 1. Alright, so our nth term can be defined by -1/3 to the n minus 1. And from there, fifth term is very easy to find. So fifth term is -1/3 to the 5 minus 1, which is -1/3 to the 4th power. So therefore, a sub 5 is going to be 1 over 81. How are you doing up to here? Hopefully you're understanding it and you're becoming one with the geometric sequence. But let's take a look at another example. Example 4, find the nth term an. Alright, so the sequence is given by -3, 1, -1/3, 1 over 9, and so forth. So first, we need to try to come up with the pattern. And the first term is -3, so we better start out with -3 times something. And it looks like we must involve the multiples of 1/3. So let's keep that in mind and let's rewrite this. I'm going to write it as -3, 1, -1/3, 1 over 9. So this is n equals to 1, 2, 3, and a 4. So let's try to rewrite this as first term, a sub 1 is going to be -3 And it better involve the multiples of 1/3. So how about 1/3 to the 0th power? So that will give us 1. So 1 times -3 will give us -3 back. Okay, now 1. How can I rewrite this? So we need to have a negative in here because our value is +1. So this is going to be 1/3 to the 1st. And the next one, I can write this as -3 times +1/3 to the 2nd. Does that work? Yeah, it does. And then here, -3 times -1/3 to the 3rd. So we got our a sub 1. So -3 is going to be our a sub 1, but we still need to able to rewrite these guys by finding a pattern. So let me see. So this is going to be, I'm just looking at what I just boxed, powers of 1/3. So here it's going to be positive, -1/3, positive 1/3, -1/3. Since this is alternating, I need to fiddle with the exponent. So no matter what, I'm just going to play with -1/3. And let's try to come up with the correct exponent. So when n equals to 1, the exponent on 1/3 is 0. When n equals to 2, our exponent on 1/3 is 1. N equals to 3, exponent is 2, and so forth. That's 1 less, isn't it? 1 less than n. So here, I'm going to write it as n minus 1. So I think we're pretty much good to go. So therefore, our nth term, a sub n, is going to be -3 times -1/3 to the n minus 1. So the way we just did it was a little bit time consuming and kind of give us a little headache. So here is another way that you can do. So let me just write that out. Okay, so we already know that if this is a geometric sequence, then our a sub n is going to be a sub 1 times r to the n minus 1. So we already know a sub 1 is going to be -3 because that's our first term. So all you have to do is find the common ratio r. So first let me write it as a sub 1 is -3. We got that much. Now let's take a look at our sequence. How's it go again? It goes -3, 1, -1/3, and 1/9. Okay, so now from here to here, how do I get, starting from -3, how can I get to 1? Well, if I multiply by -1/3 to 3, I could get to 1. Now, can I multiply the same quantity, which is -1/3, to get from 1 to -1/3? Yes, we can. So from 1 to -1/3, that's multiplying here by -1/3. And then what about the next term? If I multiply -1/3 times the -1/3, I could get to 1/9. So we do have a common ratio. So our common ratio r is going to be -1/3. I like doing this way much better. And many students ask me when they learn geometric sequence, how do I know if the sequence is geometric or arithmetic? So for geometric, if you can come up with the same common ratio or same numerical value from the first term to the second and second to the third, by multiplying, that will be geometric. Whereas for arithmetic, if you can come up with the same number, or the common difference, I should say, from the first term to the second and second to the third by adding, then that will become arithmetic. Anyways, let's do another example. Now you're given the sixth term and the common ratio. So the sixth term of the sequence is 243 and the common ratio is -3. So let's use this formula for the geometric sequence. A sub n is a sub 1 times r to the n minus 1. Now let's plug it in our common ratio. So we have a sub n equals, we don't know the first term yet, and here you're going to have negative 3 to the n minus 1. So to find the first term, you're already given that the sixth term of the sequence is 243. So let's replace our n with 6. So here we go. A sub 6 is a sub 1 times negative 3 to the 6 minus 1. So this is going to be a sub 1 times negative 3 to the 5th. What the heck is that? So that's a sub 1 times negative 243. Okay, but we already know that a sub 6 is 243. So I'm going to set that equal to 243. That's a 4. Okay, so that what do we have then? So that implies that we have a sub 1 times negative 243 equals 243. So dividing by negative 243 on both sides, then we get a sub 1 is negative 1. Okay, so I think we are good to go. So therefore, our a sub n is going to be a sub 1, which is negative 1, times r is negative 3 to the n minus 1. And that's our answer. Our next topic is geometric infinite series. So let's go with the definition. Series, let's just call it L, equals sum k going from 1 to infinity of a sub 1 times r to the k minus 1. We say that it converges if L is a finite number, meaning not plus or minus infinity or not oscillating, meaning it's gonna go to 2, negative 2, 2, negative 2, 2, negative 2, and it's never gonna converge to one numerical value. And otherwise, we say that it diverges if L is plus or minus infinity or L does not exist. L does not exist means what I was just talking about, 2, negative 2, 2, negative 2. So where is it going? Is it going to go to 2 or is it going to go to negative 2? We don't know. So in that case, we say that series diverges. The next theorem is very, very important. Memorize this. Convergence of an infinite geometric series. It says that if absolute value of r is less than 1, the infinite series converges, and if it converges, we got lucky. We could actually compute the infinite sum. The formula is a sub 1 divided by 1 minus r. Difference between what we have done so far and for this infinite series is that, of course, k is going to start from 1 to infinity instead of stopping at some numerical value n. But do you realize that if it stops at n, then since there are finitely many terms, you can keep adding it and get the actual sum itself. However, this series is going up to infinity. So it's going to be very difficult to compute the actual sum itself, infinite sum itself. But this is so cool because as long as it's geometric infinite series, we're able to compute the sum. Sum's going to be a sub 1 over 1 minus r. Let's do some examples. Example 5, determine whether the infinite series converges or diverges. If it converges, find its sum. So let's go with part A. Sum k going from 1 to infinity of 5 times 1/4 to the k minus 1. So let's make ourselves a note again. Sum k going from 1 to infinity of a sub 1 and r to the k minus 1 converges if the absolute value of r is less than 1. And if that is so, then we're going to have the sum being a sub 1 over 1 minus r. Okay, so our 5 is our a sub 1, and 1/4 is going to be our r. So let me just write that out. So we have a sub 1 equals to 5, and the absolute value of r is absolute value of 1/4, which is 1/4. Last time I checked, 1/4 is less than 1. So that means that according to the theorem, therefore, series converges. That's my shorthand notation for converges. Okay, so that means that we should be able to compute the sum. So I'm going to say with sum being a sub 1, which is 5 over 1 minus 1/4. So this is going to be 5 over 3 over 4, which is 20 over 3. Let's take a look at another example. Sum k going from 1 to infinity of 1/2 times 3 to the k minus 1. So let's apply the theorem above. So 1/2 is our a sub 1, and our r is going to be 3. And let's check our absolute value of r, which is absolute of 3. Last time I checked, that's 3, and this is going to be greater than 1. So according to the theorem, series diverges, which means that if you keep adding those terms of numbers, it's going to go up to infinity. But let me just box that for the answer. And let's do another one. Okay, so for this problem, you need to be careful a little bit. Do you notice that this is not quite officially geometric series? In order to be a geometric series, if k starts from 1, the exponent on r must be k minus 1. So this series is starting from k equals to 1, but our exponent is just k. So we need to somehow able to rewrite this as an exponent of k minus 1. So let's take a look at this. So let's call this one a side work. 3 over 4 to the k. Do you see that this is same thing as 3 to the 4 to the first times 3 over 4 to the k minus 1? Because you'll be adding the exponents. So if you add the exponents, 1 plus k minus 1, that should just give you a k back. So now what we're going to do is we're going to rewrite this series. Okay, so now let's talk about a sub 1, the first term. So the first term is going to be the product of these guys. Okay, so our a sub 1 is going to be, what value is that? 3/2. And our r is going to be 3 over 4. So I think we're good to go. Let me just try to rewrite this a little bit prettier. So here you're going to have sum k going from 1 to infinity of 3 over 2 times 3 over 4 to the k minus 1. So, okay, so this guy converges because our absolute value of r is absolute of 3 over 4, which is 3 over 4, which is less than 1. Okay, so therefore it's going to converge. Now you're going to have to find the sum. Easy peasy. Is a sub 1 all over 1 minus r. So a sub 1 was 3 over 2. Now whole thing over 1 minus 3 over 4. So this is going to be 3 over 2 all over, what is that, 1/4? So this is going to be 3 over 2 multiplying here by 4 over 1. So what the heck is that? 6. Alright, so that's our answer. Alright, so let's do another one. Please pause your video and try this problem on your own. Okay, so I'm gonna assume that you paused it and tried it. So let's go over it. So in this case, our exponent is good to go. It's k minus 1 and k starting from 1. Awesome. So here we have a sub 1 is 3 and our r is negative 3 over 2. But be careful, we're analyzing the absolute value of r, right? So the absolute of r is absolute of negative 3 over 2, which becomes positive 3 over 2. And this guy is greater than 1. So according to this theorem, our series diverges. And now I'm going to shut up and I'm going to stop right here. I hope that you're getting kind of hang of it, learning about the sequences and series. Those of you who's going to move on to calculus, you'll learn this again in more in depth in second semester calculus. But again, if you have any questions, please let me know.